Okay, so far we've looked at mole to mole, which takes one step, mole ratio type problems. Then we did mole to something, or something to mole is only going to take 2 steps because you have to do a conversion step and then you have to do the mole ratio step. Well, number 3 up here is an example of mass to mass, which is something to something. Now remember, there's 3 types of things we can convert to the mole. We have grams, we have liters at standard temperature pressure for a gas, and we have the particles, the Avogadro's number, 6.02 times 10 to the 23rd. Here, though, we're going to be doing grams to grams, but basically setting up the same type of T-chart, being able to calculate the different quantities of different chemical species in the chemical reaction. So looking at this example, we have copper reacting with silver nitrate, that would be these two, okay? What will be the number of grams of copper required? So this is the one we're missing. We don't know how many grams that is. To produce 432 grams of silver. So this is the one that we know, 432 grams. Now, we plan it out using our map. So we are able to go, starting here with our grams of our silver. And we have to also put the unit and the substance because now in the middle we're going to switch over to the copper. So we do have to identify the different chemical species as we're going. But from grams of silver, the only thing we can go to from there is directly to moles of silver. We have to do that conversion step first, where we're going to go from grams of silver to moles of silver. Once we're in the mole, once we're there, now we can switch to the moles of the copper because we can do the mole ratio. So at this point is where we can switch over to the new substance. And from going from grams of silver to moles of silver to moles of copper, then at the very end we can change those moles of copper back over to grams. So that's going to be the last step here, is changing right here to grams of copper. This basically, you can set it up this way, where you decide everything that's pretty much going to go on the top of the T-chart. So here's our T-chart. Okay, setting up our fractions. So grams of silver to moles of silver, moles of silver to moles of copper to grams of copper. Now it just becomes the setting up the dimensions for the conversion and for the mole ratio. And remember, we set these up so that we're basically multiplying fractions, equivalent fractions here. So we can take, we've got to get rid of our grams, so that's going to go down, the diagonal down there. So the grams of the silver go down here to cancel. And we can easily go from grams of silver to moles of silver. It's a simple conversion, molar mass, using the periodic table. And then we can take this, the moles of silver, we diagonal those down. We go to the moles of the silver here. And then we can use the mole ratio in the balanced equation, the coefficients, to change over to moles of copper. And then last but not least, we take our moles of copper, put those down here, and then we can change those moles of copper to grams of copper. So this is a conversion step right here. This would be a conversion. We are just going from grams to moles using our mole map and the periodic table. So 1 mole of silver, we look at our periodic table, is going to be 107.87. Okay, all you have to do is have that periodic table out to reference. Now this part right here is the mole ratio part. This is where we need to look at our balance reaction. So we look up here at the 2 in front of the silver. There's a coefficient of 2 here, so we're going to put that next to the moles of the silver. Over here, there isn't a coefficient in front of the copper, so that means it's an understood 1. So we put the 1 on top next to the moles of copper. This is the only time where we're using the coefficients of the balanced reaction is when you're doing the mole ratio. Last but not least, this last step right here is also a conversion. Now we're just converting back from moles to grams. Using the periodic table, we need the molar mass of copper. So go ahead and take a moment to refer to your periodic table. Conversions always equal 1 mole of the substance. And if I'm looking at the one here in my classroom, it says it's 63.55 grams equal 1 mole of copper. And now that we have all of the lovely dimensions set up and we're able to cancel, and you can double check and make sure everything's set up right, because the grams of silver should cancel with the grams of silver there. The moles of silver should cancel with the moles of silver. And then the moles of copper cancel with the moles of copper. So what are we left with? The grams of copper, which is what we want. Then it's just multiplying fractions. That's really all we're doing here. Multiplying fractions. What I do in my graphing calculator is I multiply the top, and then I hit enter, and then I just start dividing by everything on the bottom. I think that's easier, although you could use parentheses for multiplying the 107.87 times 2 on the bottom. So let's go ahead, calculate it. 432 times 63.55 divided by the 107 divided by the 2. Now we're going to get our answer over here. I'm just going to write out a calculator answer. Okay, so this is what should appear in your calculator. That's not the correct final answer, though, because we always have to consider significant figures at the end there. So we look at the measured value that we began with over here, 432. How many significant figures does that one have? 3. So that means the answer should also only have 3. And you always start from the left to count your digits. So 1, 2, 3. Do we round up that 7 or leave it a 7? Leave it a 7, good. Now don't forget to write the unit and the substance. Unit, substance, final answer. And this is the long one, the 3-stepper. Why does it take 3 steps? Because you have to convert to moles first. Do the mole ratio to switch to the new substance, and then you have to convert it to something else at the end. All right, so let's see if it will do the recap now. Just to process it one more time, just kind of work through the PowerPoint, and if you need to go back, it shows you exactly the steps that I just did, as well as you can always watch it on YouTube. So here's our map again, starting with the grams of A. Got to go to the moles of A to get over to the moles of B, which happen to be the copper, and over to the grams of copper. Kind of sets up the top part of the track for you, and then you can diagonal down the other things to make them cancel. And then you just insert your numbers. So the molar mass of silver, that's going to equal 1 mole of silver. Now we got to do the mole ratio. Look at the balanced reaction. We've got 2 moles of silver to 1 mole of copper. And then one more molar mass conversion. The 1 mole to 63.55. Check for canceling. And we get our final answer. This one nicely color codes it too, because it has the A's, what you're starting with, moving over to the B's, which is what the substance that you want to find. All right, so this one is also a something to something. I'm going to give you a couple minutes to try to set it up on your own. It's particles to liters, because you're starting with formula units of the calcium carbonate, so 4.25 times 10 to the 24th formula units. And then it says how many liters of carbon dioxide. So this is what you're trying to find, the liters of the carbon dioxide at standard temperature pressure. I'm going to give you a minute or two to try to set it up, and then we will come back and go over it. Okay, so let's go ahead. Looking here, we're starting with formula units. So we have to change those formula units into moles. And formula unit would be a type of what? Type of particle, very good. So which number are we going to use there to convert? Avogadro's number, good. So I'm going to start all the way over here, because a lot to write. 24, formula units, CaCO3. Okay, from there, we're going to change that over to moles of calcium carbonate. And from the moles of calcium carbonate, what's the next step? Where do we go to? Moles of carbon dioxide. Very good. You guys are picking this up good. And from the moles of the carbon dioxide, then we go to liters of carbon dioxide. Good. Now, what you do is fill in our chart. Okie dokie. So we diagonal down those formula units. Put them down here. Formula units. CaCO3. Take these, put that down. And the last is putting down the moles of the carbon dioxide. And we just insert our numbers. As said, formula units is a type of particle, so we use Avogadro's number here. Times 10 to the 23rd, that equals 1 mole of the calcium carbonate. Now the second step is looking at the moles in the balanced reaction. So what's the moles here for the calcium carbonate? That's an understood one, so 1. Same thing over here for the carbon dioxide. Since there's no coefficient, it's an understood 1. And then last but not least, the conversion step over here. What's the number for liters? How many liters equal 1 mole at standard temperature pressure? The 22.4 equals 1 mole. Very good. So here is the conversion step. This is the conversion. Here's the mole ratio in the middle. You're going to see this pattern. It's going to start to look like that every time. And then the other conversion over here. All we have to do now is calculate. You can check, make sure things cancel, like formula units, moles of calcium carbonate, moles of carbon dioxide. And now we can go ahead and get our answer. Multiply the fractions. Times the 22.4 divided by Avogadro's number. Here we go. And if we're looking for significant figures, like we always should be, we have 4, 2, 5. That means we should have how many in our answer? 3. Okay, so calculator answer looks like 158.1. So we're not going to round up the 8. That's liters, carbon dioxide. Final answer. Any questions? All right. Let's look at the steps one more time. Go through them pretty quickly. Formula units to liters. Looking at your map, we're starting with particles this time, going to liters. Set up the top of the chart, let it flow. Then you can start getting the canceling out. Add your numbers to the fractions and multiply, cancel, all that good stuff. Still going to end up with 158 liters. But like I said, if you need recap on the steps, they're here in the PowerPoint. And like I said, you can check out YouTube. Now we're going to talk about percent yield. Percent yield is a different concept, but you have to use stoichiometry to find it. So let's talk about, first of all, what is percent yield? What does it mean? Well, what we've been doing, the stoichiometric calculations where we say 432 grams of silver equals this, how many grams of the copper were needed to produce that. Well, this is, of course, if the reaction is 100% and you don't have to worry about any other factors, like the reaction completely ran, every single thing entirely reacted. That's the ultimate, like, this is the best you could possibly do kind of answer is from the stoichiometry. Like, if everything was perfect in the lab, you should get this number. However, in the lab, you rarely have perfect conditions. That's just a given. So the likelihood that you would hit 100% yield is very small. And for some reactions, if you can get in the 60s, you're doing pretty well. If you remember from collision theory, they have to collide with enough energy, and then they have to collide with the right orientation. So a lot of times, some of your reactants don't ever react. And that's why we wouldn't get close to achieving 100% yield. So it tells us how successful the reaction is. The closer you get to 100%, the better. Obviously, that's more product and less wasted reactants. So it's the ratio of the actual yield, like that's the one from the lab, the experimental, like you did it in the lab and this is what you got, compared to the theoretical. The theoretical yield is the one that you get from doing the T-chart and the stoichiometry. The stoichiometry tells you, like, if everything's perfect, this is what you should get. But the experimental is rarely perfect and is rarely going to hit that mark. So lab, experimental, theoretical from the calculation. Experimental over theoretical times 100 gives you your percent yield. All right, so here's our first example. This one's nice and easy because they don't make you do any extra calculating, because they tell you what the theoretical yield is. When potassium chromate is added to solution containing silver nitrate, solid silver chromate is formed. From our calculation, the reaction should produce 0.488 grams of the silver chromate. After doing this, Sally obtained 0.455 grams of the silver chromate. Calculate the percent yield. So the first thing when you read the word problem is you need to identify the experimental, or the one that was done in the lab, versus the theoretical, which is the one from the calculation. And hopefully you have enough of the context clues here to figure that out. So which one is the theoretical? Correct, the 0.0488 grams. This one right here should produce, that's if everything goes perfectly, that's what it should give you, okay? And the other one over here, the one that Sally got in the lab, Sally obtained, that's going to be your experimental. Like so, okay? Now all you have to do to calculate it is do the experimental over the theoretical times 100, like so. Then you get your percent yield. So what do we get here for our percent yield? And how many digits should we have in our answer? 3 digits, good, and 93.2 is correct, or that's the one I got, 93.2%. Very, very well. So this one has 3, because remember that 0 doesn't count. This one has 3, that 0 doesn't count. Since we're dividing, we go with least number, and and that's where we get those 3 digits for our percent. This is just an easy one. We're showing you like figuring it out from the word problem and doing the actual like just formula. Not all of them are this simple. Actually, most of them aren't this simple. So, but recapping here for you, there's your equation. Stick it in there and you get your answer. This is more like the problem that you will see like on a quiz type problem. Percent yield 2-part problem. It's a 2-part problem because instead of giving you the theoretical yield, what are they giving you here? Well, they do give you the experimental, definitely. They will always tell you that part, how much was obtained in the lab. What is the experimental up here? 41.7 is correct, so that's our experimental. However, what's the other number that they gave us? They didn't give us the theoretical. What did they give us instead? They gave us 29.7 grams of KOH. And guess what KOH is in the reaction? It's one of the reactants, right? So this is the 29.7 grams. What are we looking for here, though? We're looking for how much of the potassium sulfate has been produced. So now, guess what we get to do? Figure out, if everything's perfect, how much potassium sulfate should get produced. So this one requires us to do a T-chart. We have to do the stoichiometry. We have to figure out the theoretical yield. So go ahead and take a moment to set that up. It's a grams to grams, so it's a something to something. Go ahead and take a moment to do that. Okay, let's go ahead and set this up. So, starting here with our 29.7 grams of the potassium hydroxide. Then we got to go to moles of the potassium hydroxide. Then we can come over here to do the moles of the K2SO4. And then we can get over to grams of K2SO4. And set up our T-chart. All right, so grams go down here. The moles of KOH down here. Just diagonaling them down like so. And this one down here of the K2SO4 moles. Now we insert our numbers. KOH, though, we have to calculate the molar mass from the periodic table. So here, I'll do that over here. K is 39.1, O 16, and H 1.01. Let's add those together. Remember, I want everybody to do their molar masses to 2 decimal places. That way we all have the same molar mass. 39.1, 16, 1.01. Did you get 56.11? Yeah. All right, good. That equals 1 mole of KOH. Good. So this is the conversion step. Now we look at the balance reaction. We have 2 moles of KOH. Goes down there. Here, there's nothing, so it's an understood 1. Goes right there. So here's our mole ratio step in the middle. Then I also have to do, oh fun, the molar mass K2. So K 39.10 times 2. Sulfur is 32.06, and there's only one of those. And then the oxygen, 16 times 4. So put all this in your calculator and add it up. Find the molar mass of that. Did anybody get that molar mass, by the way? What is it? 26, all right, 174.26, everybody got? You all in agreement? Yes? Okay, good. All right, now we're all set up, ready to calculate 29.7 times 174.26 divided by 56.11 divided by 2. Now, how many significant figures should we keep in our answer? 3, exactly right. Okay, so I'm getting 46.1 grams K2SO4. Guess what that is? This is known as the theoretical yield. Right there. So that goes right here, the 46.1 grams. Now we can do our lovely calculation. So we have the experimental over the theoretical times 100, 41.7 over 46.1 times 100. And what do you get for your percent yield? 90.45. That's the calculator answer. Since both of these have 3, right? Let's keep our percent to 3, so 90.5 good for me. Very good. 90.5. You guys get all that at home? You're all doing okay? Not seeing too much in the chat there, so everybody hanging in there? Yes, okay, good. Sounds good. All righty then. Here we go. And that, yes, is the correct answer up here. The answers are in the PowerPoint. They're kind of written over right now. But that's the gist of percent yield. So percent yield, basically what they're going to give you usually is one of the reactants. Then you have to calculate the theoretical yield of the product using stoichiometry. And then they give you somewhere in the word problem too how much was made in the lab, which will be the experimental. So these problems will pretty much follow this same type of pattern, just like this one up here.